So check. Last class, if you remember, we discussed about special electron configuration of special elements like chromium or copper. We learned that when it comes to chromium, the atomic number, which is 24, should have expected electronic configuration this way: 1 is 2 till 3d4. But unfortunately, the actual electronic configuration you would notice in the outermost orbits is 4s1 and 3d5. And I explained you this can be compensated, or why this configuration is valid where it is violating the off-Bose principle is based on a terminology called exchange energy. Exchange energy is the energy that is released when an electron is been added to a particular orbital where an already existing electron is present. That means you're trying to pair it up. So pairing always requires energy. And if that energy which is required, correct, is more than energy required to excite an electron. That means if an electron has to excite from lower energy to higher energy, if that energy is lesser than the pairing energy, then why would it prefer to pair itself? It would rather go to the higher orbit. And that's exactly what happens in chromium and copper cases. You can see exchange can be explained on the basis of how much easily electrons can move around degenerate orbitals. Degenerate in a sense, orbitals having same energy. Now this orbital and this orbital have same energy. If this electron moving into the other orbit and this electron moving into the first orbit, when they move around, they do not require any energy because they both are present in the same energy frame. Hence, this movement of electrons helps in throwing away some energy and getting more stable state. So more the number of exchanges a degenerate orbital can handle, more is the stability an atom can get. And that's exactly what happens in the case of chromium, that when you have four electrons in the degenerate orbitals, it's able to get six exchanges. But imagine if one electron from 4s excites to this 3D orbital, then from 6, the number of exchanges have increased to 10. So the energy that electron is spending to make this excitation from 4s to 3D, if that energy is less than the amount of exchanges that it is offering, correct, then it will definitely then it will definitely go for exchange energy, correct. So exchange energy is the amount of energy that is released. So there are two energies. One, if you pair the electrons, energy is required, but if you exchange the electrons, energy is released. Got it? So instead of keeping itself in pair, it can the electron can excite to the higher orbit, and that way it can release more energy and get stability. Of course, can it happen in all the orbitals? Not so much. It would happen when the difference in the energy, exchange energy, is at least 3 to 4 units. You can see 6 here, 10 here. The difference is 4 units. When 4 units of difference will come, then the configuration changes. So it will be 4s1 and 3d5. Now the same logic is applied even in the case of copper. Copper's number of electrons are 29. Electronic configuration goes from 1s2 all the way to 3d9. And now notice again, when it is 3d9, already there are 9 electrons. See, the electrons which are in this particular spin, upward spin, they can exchange electrons like this, and those number of exchanges are 10. And the electrons which are in this particular spin, they can exchange among themselves, and those number of exchanges are 6. So total we have 16 electrons conventionally if the configuration is 4s2 and 3d9. But if it was 4s1 and 3d10, even the ones which are like this, now there are 5 of them. 5 of them will make 10 exchanges. In total, we got 20 exchanges. And the difference here is 4 units, which means copper can also be expected to handle a configuration like this, which is 4s1 and 3d10. Okay. Usually, guys, the energy difference between P, D, and F is less. That's where the electronic configure, I mean, that's where this exchange energy makes more sense. But if you are comparing something about 2s 2p, 3s 3p, electrons exciting from 3s to 3p or 2s to 2p, that becomes little difficult because the difference in the exchange, difference in the energy level is higher. Hence, whenever you see an electrons are unpaired but half filled in D or F or P, which means they're handling more amount of exchange energy. Hence, we say half filled stability is more stable. Similarly, in the copper, you can see all of them are completely filled, so full filled stability is also more stable. So wherever there is a half filled or a full filled, the stability always increases. Is this point clear? Right? Now, coming to the next part, whenever we have elements, we should know how many number of unpaired electrons they are carrying in their neutral form, in their cationic form, in their anionic form. For instance, if N2 minus is given to you, so first, what do you mean by 2 minus here? See, when it is given as N2 minus, it meant originally the configuration of nitrogen is 1s2, 2s2, and 2p3. But now I'm adding another 2 electrons to it. So if you add another 2 electrons, electrons are always added to the outermost orbit. So the outermost orbit is 2p, so it will become 2p5. So the 2 minus always signifies there are more number of electrons than protons. So this will be the new configuration for N2 minus. Just for the sake of understanding how many number of unpaired electrons are there, I would write it in terms of blocks. So there are 2 electrons in this box and in this block. And you know that 2p is a set of 3 blocks. And you have 5 such electrons. 1, 2, 3, 4, 5. So you could notice that the number of unpaired electrons are 1. Okay? Just a second. Sorry. Check. So the number of unpaired electrons are 1 in this case, everybody. Clear? If the question was given about, sir, what about the number of unpaired electrons of nitrogen? Then I would have said 1 is 2, 2 is 2, 2p3. And if you write the blocks for it, it will be shown that there are 3 unpaired electrons in this case. So number of unpaired electrons are 3. Okay. Likewise, helium 2 plus. So check it out. If it is about helium plus, sorry, 1 helium plus. Helium has supposed to have 2 electrons, which is 1s2. But now the plus signifies that I have removed 1 electron. So minus 1 electron, which makes it 1s1. That is the configuration. And since it is only 1 electron, so therefore number of unpaired electrons are 1. Likewise, iron. Iron is 26. The configuration is argon. Up to argon, you know, there are 18 electrons. Then it is 4s2, 3d6. If I put this electrons here, which is 4s2, and we have 5 orbitals here like this. So 1, 2, 3, 4, 5, and 6. These are the 6 electrons we have. Right. Check. So we know that we have initially when only iron is there, the number of unpaired electrons are 4. So you can clearly notice that 1, 2, 3, 4. These are the number of unpaired electrons. But if we have been given Fe plus 3, that means I have to remove 3 electrons. Now, where do I remove those 3 electrons from? Remember that electrons removing should be always done from outermost orbit. That outermost orbit may or may not have higher or lower energy. We don't need to check that. We just need to check whether it is outermost or not. So between the third shell and the fourth shell is always the outermost. So you would remove the electron first from the 4s and then only you will enter into 3D. So first 4s. So 4s will now become 0. So the configuration now will be argon 4s 0 and then we have 3D. How many electrons? Because 2 electrons have gone from 4s. One more electron I remove it out. So when I remove one more electron, this will become 3D5. So now 4s is completely empty. 3D5 you have to reorganize once again. So if I reorganize that, I'll get this as 1, 2, 3, 4, 5. So now the number of unpaired electrons are 5. So originally we had 4 unpaired electrons before removing. Now if the question is about Fe plus 3, how many number of unpaired electrons do we have? Now we have 5 unpaired electrons. Clear everybody? Same goes with cobalt also. I'm directly writing now. Check out when it comes to cobalt plus 3, right? So it has 27 electrons and protons. So configuration is originally supposed to be argon 4s2 and 3d7. But since I have to remove 3 electrons, 4s will go away, 3d will go away. So you will get this as 3d6. So 4s, we have 0 electrons here. And in case of 3d, 1, 2, 3, 4, 5. So we have 6 electrons here. So out of which number of unpaired electrons are 4. Okay. And lastly, zinc. If you notice that zinc 2 plus, zinc supposed to have 30 electrons and protons with the configuration of RS4 is 0 and 3D10, right? Because 4s electrons have been gone. Therefore, in the case of 3D, we have to distribute 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number of unpaired electrons are 0. Correct? Now notice something very interesting. When number of unpaired electrons are 0, right? Number of unpaired electrons are 0, which means electron which is rotating on its own axis is supposed to give some amount of field around it. I told you this in the last class. Let me remind you. If this is an electron, and let's say this electron is rotating across its own spin, so it is expected to create a field around it. It will create a field around it like this. And the field lines which it will have a direction like this, let's say. Okay. Now, suppose if you have another electron here, which is rotating in anti-clockwise direction here, or rotating on its own axis in anti-clockwise direction, that is also supposed to generate a field around it, correct? And in the field, you will notice that it will start moving in this direction, correct? Here, like this, in this direction. So what would happen here is, whenever there is a field happening here, so if this vector, basically, if an electron goes here, current will go in this direction. If an electron goes here, current will go in the opposite direction. So when you notice the electron here, whatever the field this is generating in this direction and this direction, they will both get cancelled off. Okay, sorry, I wrote the both clockwise only here. Let me write anti-clockwise. Yeah, no, it's anti-clockwise only. Anti-clockwise, clockwise. Yeah, yeah. So if you notice that, you will have a clockwise spin like this. Okay. So you would notice that when there is a clockwise spin here, this is how the flow direction of the electrons field is. And this is the direction of electrons field is. So if I bring both of them together, what should happen? The fields will get cancelled with each other. That means their force, the magnetic field which it is generating on both directions will get cancelled. So net magnetic nature would be observed almost zero. Such kind of cases where the number of unpaired electrons are zero, we call those species as diamagnetic species. In fact, if electrons are being approached, so remember this, if this entire, let's say this entire species which has a nucleus like this here, and this has various orbits here, and within that orbits we have some electrons here, in that we have some electrons, okay, and this entire species is brought close to a magnetic field, an already existing magnet here like this. So imagine there is an existing magnet here. So you know how the magnetic field lines will be. This is how the magnetic field lines are. Okay. So imagine if you start bringing this species close to magnetic field this way, it starts coming close to the magnetic field here. Correct? If this species net number of unpaired electrons are zero, then they do not get attracted to the magnet. On the contrary, if they start moving out, they get repelled. They get repelled here like this. Got it? It will start moving away from it. Why? Because there are no unpaired electrons which will match their field with the magnetic field and try to come closer to the magnet. Okay. Now, such type of species we call them as diamagnetic species. So, a species with number of unpaired electrons are zero are called as diamagnetic species. Species. Species means it could be neutral or it could be ion, anything which does not have any unpaired electron will be feebly repelled in magnetic field. Okay. On the contrary, if you have any unpaired electron, we call them as paramagnetic species. Correct? So if they have feebly attracted to magnetic field due to presence of unpaired electrons. Due to presence of unpaired electrons. Okay. So please check this case, everybody. I hope you guys understood. What is the importance of unpaired electrons here? Any doubt? Swami, did you follow this beta?
Yes, sir.
Right. Dev, Kapil, Manav, all good beta?
Yes, sir.
Yes, sir.
Right. Now, there is one aspect that we need to learn is that whenever there is an electron moving, either it is moving from one point to the other point or it is moving on its own axis. Every movement possesses something called momentum, right? If an object is moving from point 1 to point 2 without rotation or without vibration, then we say it is getting translated and it will carry linear momentum. It will carry linear momentum. Okay. As per Newton's second law, if if you do not stop it by any other external force, it tend to be always carrying that linear momentum, correct? And that is called the moment of inertia. Okay. So it will continue to be in that moment only. So that's what we are trying to explain here in the in the form of momentums. So there are mainly three types of momentums which are observed within the atom. One, orbit angular momentum. Of course, if an electron is moving in an orbit continuously, that orbit itself is carrying some angular momentum because, first of all, it is moving in an angle, in a circular path. Hence, this Bose has already derived as mvr, and he derived the formula as nh by 2 pi. So this is angular momentum, and the angular momentum formula is nh by 2 pi. So it is only formula based, we don't have to derive it again. Second, there is one more momentum that is observed is within the orbital. You know that there is a particular shape of the orbital and there are electrons present in it, they are moving within the orbital. So that entire orbital also possesses some angular momentum. And this time the formula is slightly different. It is more of a vector quantity and it will be written as under root of L into L plus 1 h by 2 pi. Now, let me remind you the n here signifies principal quantum number. Principal quantum number. And it starts with the value 1, 2, 3, and so on. Every number represents that respective orbit. While here the L represent azimuthal quantum number. Azimuthal quantum number. Its value starts anywhere from 0, 1, 2, 3, and so on up to n minus 1. Okay. And lastly, when electron is moving within the orbit, right, in an orbit, within the orbital, it might also have its own spin. So we have something called spin angular momentum, which is S, and that is equal to under root of S into S plus 1. And what exactly is this small s and capital S? Capital is the angular momentum. Smallest represent the presence of number of unpaired electrons. So that is number of unpaired electrons into half. Okay, so that gives us spin angular momentum. Got it? So this is small s represent number of, sorry, small s represent sum of spins of number of unpaired electrons. Spins of number of unpaired electrons. Got it? For example, usually how the JE questions are asked. JE question typically use this terminology, that is orbit angular momentum, orbital angular momentum, or spin angular momentum. If it is been asked to the last orbital Fe plus 3, so then how do we do this? Check out. We learned the configuration of Fe plus 3 just now. Fe plus 3 has a configuration as argon, 4s0, and 3d5. So last orbital in a sense we are talking about 3d. Now we are talking about 3d. It has 5 electrons. So 5 electrons are distributed this way. We have 5 unpaired electrons here. So number of unpaired electrons are 5. Correct. And the n value of this orbital is 3. The L value, see, L value depends upon which subshell it is. D subshell has the value of 2, correct? 0 is for S orbital, S subshell, 1 is for P subshell, and 2 is for D subshell. So now we know that N value, L value, and number of unpaired electrons value. And you know that what will be the S value? It will be number of unpaired electrons into half. So that makes it 5 into half. So that is 5 by 2. Now we know all the parameters. Now simply we need to calculate the value here. So orbit angular momentum, which is also written as mvr, that is equal to nh by 2 pi. So if I have to substitute the values, what would I get here? If I substitute the values, I will get this as n value is 3h by 2 pi. So this is the answer you need to give. Got it? Second, orbital angular momentum. Orbital angular momentum, which is written as uh, L vector, which is equal to under root of L into L plus 1 h by 2 pi. So what will be that value here? Under root of L value is 2. So 2 into 2 plus 1 h by 2 pi. So that is equal to root 6 h by 2 pi. Root 6 h by 2 pi. Next, spin angular momentum. Spin angular momentum S is written as under root of S into S plus 1 h by 2 pi. And S value we already learned it as 5 by 2. So therefore, under root of 5 by 2 into 5 by 2 plus 1. So that makes it under root of into h by 2 pi. That will go as into h by 2 pi. So that comes out to be under root of 35 h by 4 pi. So this 2 will come out in the root and that will come out as 35 h by 4 pi. So a very, very standard JE question, everybody. Anything could be asked right from orbit, orbital, or spin angular momentum. On top of that, I'm adding one more factor here that is called as spin only moment. Spin only moment, which is written as mu, or the books also give it as magnetic moment. Magnetic moment, right? Moment is that force, a virtual force, which will be applied on any species when it is under the influence of a field. For example, if I have a magnet and there is some a small iron fillets somewhere near me, and if I swoop the magnet around, due to the field of that magnet, those iron particles or fillets will start moving across, right? So that is called movement. So whenever there are species present, right, whether in the form of an atom or ions, they always carry some movement around it. Got it? That means they will have that field which can cause the movement. How do we measure that movement? This movement can be measured as mu, right, which is equal to under root of n into n plus 2, and where n is number of unpaired electrons. Number of unpaired electrons. Correct? So mu here will be equal to under root of 5 unpaired electrons. So 5 into 5 plus 2, which is equal to root 35. Can you see there is a match here? Correct. So spin angular momentum will always have the multiplied value of mu. Correct. So that is mu. And mu, if that is greater than 0, that is a measure to para and diamagnetic. So if it is greater than 0, it is paramagnetic species. Correct. So if mu in some case is 0, so then that will become diamagnetic. I mean, we are measuring number of unpaired electrons only, but with a factor of moment. Everybody understood how to solve these questions? Okay, very simple formula based. I don't think it should have much difficulty. All you need to figure out is how to write the configuration, how to identify the number of unpaired electrons. Okay, next. Why won't you guys do the same thing for this question? If it is chromium plus 3, okay, please try it out. If you want, I'll write the formulas again for your reference. Please try it out. There is OAM is NH by 2 pi. O dash AM is under root of L into L plus 1 H by 2 pi. And SAM is under root of S into S plus 1 H by 2 pi. So please use this formulas. Quick. Let's see what you must have got here. Chromium being plus 3, it is supposed to have 24 electrons and 24 uh, protons. Now it has become argon 4s 0 and 3d 3. Okay. And That is the number of unpaired electrons if you may have solved it. So you would see there are only three unpaired electrons in D, correct? Unpaired electrons in D. So if by default nothing is given, you should always consider about the last orbital. So the last orbital is 3D. So in that case, the n value is 3, L value is 2. Right. So now let us calculate OAM. OAM will be 3h by 2 pi, and O dash AM, which is orbital angular momentum, will be equal to under root of 2 into 2 plus this. So that makes it root 6. So root 6 h by 2 pi. And spin calculation is number of unpaired electrons into half, that is 3 by 2. Now capital S will be equal to under root of S into S plus 1 h by 2 pi. So which makes it under root of this is 3 by 2 into 3 by 2 plus 1 h by 2 pi. Okay, so that makes it how much? 15 root 15 h by 4 pi. So these are the values you are supposed to report: 3 h by 2 pi, root 6 h by 2 pi, and root 15 h by 2 pi. Just as an added bonus, what we will do, we calculate mu also. Mu is equal to under root of n into n plus 2 Bohr magnetons. Bohr magneton is a unit. So that is equal to under root of 3 unpaired electrons, 3 into 2. That makes it root 15 Bohr magnetons, which is clearly suggesting that it is greater than 0 and the molecule is paramagnetic. The molecule is paramagnetic. Please check if you have got that. Dev, Kapil, Manav, all good, beta?
Yes, sir.
Yes, sir.
Yes, sir.
So I'm free to get that.
Yes, sir.
Now, this is the last part of structure of atom, which is to analyze the Schrodinger's equation and try to figure out, uh, a very important aspect called probability and number of nodes. Okay. Now, if you may recall, the Schrodinger's wave equation is written as psi. So psi x, y, z, which means it is a three-dimensional wave characteristic, correct? An electron, electron's behavior is expressed in the form of wave character, and that is a three-dimensional wave. And a three-dimensional, any wave, in fact, has an amplitude, and this psi is associated with that amplitude. Usually, psi is defined in a Cartesian coordinates while deriving, but Cartesian coordinates would make very difficult to solve a lot of solutions. A lot of parts of the equation. So what we do, we convert that into spherical coordinates or radial coordinates. Spherical coordinates or radial coordinates means what? See, imagine like this: if electron is present in space uh, at a distance r from the origin. Okay, origin is where the nucleus is. So from the nucleus, let's say in space, it is at a distance xyz this way, and this is where it is present. Correct. If this is a position of an electron, what would be its z component? If this is x, y, and z, what will be its z component? If this is a value, then if it is making an angle theta with the z axis, then this distance from here to here will be simply r cos theta. And you know that this value is r sine theta, correct? And if this value, if you see it from the top, imagine you're standing on z axis here, and if you see it from the top, that same projection falls on x and y plane like this. So this distance and this distance is same. Okay. And now imagine if this projection is making an angle phi okay, is making an angle phi with x-axis. Then from here to here, this distance from here to here, this distance would now become x direction. So x will be r sine theta cos phi, because this entire thing is r sine theta, and this will become cos phi. Okay. And from here to here, this distance will become r sine theta sine phi. So r cos theta, r sine theta cos phi, and r sine theta sine phi. These are x, y, z, you know, values of that point. Okay. Now listen, wherever there is x, y, z, if you put these values, right, in that Schrodinger's equation, you will end up getting two different forms, correct? Where we can separate all the radial part, where it only depends upon r. And then we can separate all the angular part, where it depends only on theta and phi. Okay, so we got two parts here now. So that's now it becomes more easier to solve. Got it? So the entire Schrodinger's equation is divided into two parts. One is the radial part, which depends on only r distance. Then it depends upon angles theta and phi. So this part is called as the radial part. And what has been observed in the Schrodinger's equation is that they depend that r, this distance r factor depends only on n and l quantum numbers, while this part, the angular part, depends upon L and ML, that is azimuthal quantum number and magnetic quantum. Okay, this is psi now. Clear? Hmm. Everybody understood? Just give me a second. See, sorry, guys. Check. So what I'm trying to say is that there is a radial part here and there is an angular part here. Now, the behavior of the psi square, and 4 pi r square psi square. These three are the factors that we need to check how it is varying with respect to the radius r. That means this one, radial part, as it varies. You're not changing angles, mind you. Without changing the angle, if you go away from the nucleus, how these three factors, psi, psi square, and 4 pi r psi square is changing. Okay, so keeping theta and phi constant. Okay, when you do that, you will get a general formula. Okay, for example, if you have a quadratic equation of degree 2, I mean, in fact, polynomial function of degree 2, we know that we'll get a general formula like this, right? Ax square plus bx plus c equal to 0. This is a general formula, correct? Clear? One second. So a general formula which has been identified for psi of radial part, I'm only writing the radial part here, correct? So that radial part has observed like this. That is some constant into e raised to power of minus some other constant into r multiplied by a polynomial function whose degree depends upon n minus l minus 1. Okay. And that into r raised to power of l. Got it? This is how the general formula comes across. Okay. Exponentially decreasing function and a polynomial function and r raised to power of l. Correct? Now, depending upon the n value, you will have the respective formula. For example, let me write down the formula here. Psi of 1s. Suppose मुझे ये formula लिखना है. That is, for 1s, how is the formula changing? So what would I write? K e raised to power of some k dash into r, right? And this entire thing power will be the n value for 1s is 1, l value is 0, minus 1, and r raised to power of 0. So what is it, beta? K e raised to power of minus k dash into r. So it is simply an exponentially decreasing function. So it is an exponentially decreasing function. Exponentially decreasing function. Okay. This is what it will be. Got it? For example, if at all I have to write, I mean, let's say I have to do it for 4p. 4p. For 4p, how does the radial part looks like? So it will be like some constant e raised to power of another constant into r that multiplied by n value is 4, p value is 1 minus 1 into r raised to power of 1. So how does this look like? Now, can you notice that this is 4 minus 1 minus 1? So you will notice here there is some quadratic equation. So that means that's why the function looks like this. K e raised to power of minus k dash into r into some constant like this. That is r square plus some constant r minus and plus some q that into r. This is the way you will notice. So you will find actually three functions. One is exponentially decreasing function, exp, exponential function. Second, there is a quadratic function. And third, there is a linear function. So it is basically a simulation of these three functions. So I hope all of you understood this part. So whenever Schrodinger's equation has to be solved, the easy way to figure out all the concepts behind this is to first translate that into radial coordinates. And then you can separate out the parts here. One is called the radial part, the other one is the angular part. So the radial part specifically looks like this. So this is only the radial part, everybody. Okay. Any doubt in this part, you can ask me again. Please let me know. Everybody understood what is radial analysis? What if I need to write the psi square value? See, imagine if at all I'm writing the same thing for psi square. Psi square 1s. So how does it look like? It will be like simply k e raised to power of minus 2 k dash r. So that means, have you noticed something? This is also an exponential function. Even after squaring, it is still an exponential function, which means Squaring does not change the uh, identity of the function. It will still be the same. Got it? But one thing it will change. Normally, when you have a quadratic equation or a linear equation, chances are the function can go into different coordinates. That means it can go positive or negative. Let me show you what I'm trying to say. What if I write the same function for, let's say, 2s? So for psi of 2s, how does the function look like? Some constant e raised to power of other constant into r into a quadratic, a linear function, right? Why? Because n is 2, l is 0, minus 1, and r raised to power of 0. So that makes it k e raised to power of minus k dash into r into, this is power 1. Power 1 means this polynomial function has to be linear. So it will be something like, some r minus some constant k double dash equal to 0. This is how. Now imagine if at all I'm plotting this for psi. Okay, imagine I'm plotting this for psi. Okay, and I'll just copy this part. Okay, so I'm plotting this for psi of 1s. Psi of 1s for, I mean, with respect to r, psi of 2s with respect to r, and psi of which one I derived here, 4p. 4p with respect to r. Correct? Now notice something here. When it comes to psi of 1s, we found only that as, here, as a simple exponentially decreasing function. So if it is exponentially decreasing function, I'm sure you may have learned in graphs that exponentially decreasing function will start like this and goes this way, asymptotic. Got it? But when it comes to 2s, right? In the case of 2s, you notice it is exponentially functioning, but at one point it should become 0. That is when r becomes k double dash. When r is equal to k double dash, this entire function should become 0. That means it will also start like this, go somewhere down, it will touch it somewhere on this x-axis, and again turn around and go like this. Okay, so where does it touch exactly? It will touch at a distance of k double dash. Got it? So that will be the psi of 2s. Now, if at all I have to find out the psi of 4p here, how do I find 4p? In the case of 4p, you will notice that it is exponentially decreasing, correct? And the power is, sorry, here, the power is 2. So that means you should dip that on the x-axis 2 times. And then there is a linear function also. So notice one thing, when r is equal to 0, that is the first point, right? So that entire function will become 0. So this function actually starts like this. From here, it will start and then it touches one time where the roots of the quadratic equation is observed and goes down, touches second time, goes up, and then again it will start going down like this. So by the way, for this function, this is how the graph looks like, everybody. Okay, notice one important aspect here. When it comes to p orbitals, right, 4p, 5p, 6p, 7p, 2p, or if you have d orbitals, 3d, 4d, 5d, 6d, 7d, all of these d orbitals, or you have f orbital, 4f, 5f, 6f, and all of these orbitals, they always start from the origin. The radial graphs will always start from origin, except for s. S always starts from a particular value at this origin. Okay. And now what if at all I have to square it? So I'm taking the same graphs, everybody, and I will just simply square it here. So that is psi square here. Correct. So look into this. Psi square here, psi square here, and psi square here. So what would happen, in this case, there is no change because exponential it is still the same and everything is in the first quadrant only. But in the second case, you notice that when the function is going here, right, in the negatives, in the negative quadrant here, because when you square it, correct? So what should happen here? when you square it, whatever that is going to be in the negative quadrant will suddenly convert into the positive quadrant. So from here, the graph will change. So up to this point, it will go straight. Up to this point, it will go like this. See, I don't do that. Okay. Up to this point, it will go like this. Okay. And then from here, it will changes to this part. And then it will go like this. Only that change. So whatever that is in the negative quadrant, that will change. Here, one second. Sorry. Check. Now the third graph. So in this part also, have you noticed this is the only part which is going in the negative value. So that will go in the positive part. So I'll just remove that part and it will start becoming the positive part. Okay. This is how the graph will vary. Clear everybody? Please check this out. So whenever you have the radial part, how do we need to plot it? I hope you understood this, right? Now, the last important part, which is 4 pi r square psi square. If you plot that, what would happen? Got it? So imagine if at all I have to plot this as 4 pi r square psi square. Okay. 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 So how do we make this here? Sorry. So check it out. So if you have to make the new function here, which is as 4 pi r square psi square. Correct. What is its significance? I'll tell you. First, let us plot the graphs. Okay. So then imagine that what will happen to the 1s orbital now. So this for 1s, for 1s, how does the graph look like? How does the formula look like? So 4 pi r square psi square, 4 pi r square psi square would look like this: 4 pi r square into some constant into e raised to power of minus 2k dash, if you remember, 2k dash into r. This will also become square. But you know that these are all constants only. So suddenly now the graph will have two new functions. One is an exponentially decreasing function. The other one is a parabolic function, correct? Okay. Y is equal to x square. What is it, beta? It's a parabola, correct? Isn't it? Clear? It's like a quadratic form, but only one parameter is there. That means it will become parabola. So we will have an exponential function and a parabolic function. Got it? Second thing, if you do the same thing for, let's say, 2s, you do it for 2s here. For 2s, the same function, 4 pi r square psi square, that will become 4 pi r square into k square into e raised to power of minus 2 dash into r into, I was getting a linear function, something like r minus some k double dash, that will become also square. So this is the function. So again, you will have exponential function and again a parabolic function. This will help us to understand it will dip or it will touch on the axis here. Okay. So this is also a quadratic function, which will help us understand that it will dip at that point. Okay. Now, if I plot that, there is a particular pattern you will understand here. So there is a simple pattern that you will notice. So let me plot that here. Okay. If I take this, show it here. So all I need to do is make this as 4 pi r square psi square, 4 pi r square psi square, 4 pi r square psi square. Okay. Now the pattern is a parabolic function and an exponential function, decreasing function. That's a very important pattern. You'll be learning this in the higher studies as well. Okay. The pattern is, it will appear something like, a bell curve, a bell. So how does a bell go here? So it will start from here. Sorry, it will start from here. It will go to the peak and then comes down this way. This is the way it will be appear. Same thing goes in the next case also. Correct. In this case also, if you notice, it starts from here, touches once. Why it is touching once? Because of this value. Because this will make it to touch at some k double dash value. And from there, again, it will raise, it will go and go this way. You'll have two bells. And the last case. In the last case, you notice that n minus L minus 1 value. Everybody go here and check. When we discuss 4p, we got a quadratic equation. Quadratic equation means we have 4 minus 1 minus 1, which is 2. N minus L minus 1 is 2. So now the same bell curve touches two times. Once, twice, right? So this is how the graph will go. Got it? So one thing to notice here is the peaks will continuously increase here. The peak values will keep increasing here. Okay. What is the great thing about this graph is that when Schrodinger's analyzed that the value of the peak where it is matching for hydrogen, especially if you notice for hydrogen atom, this is matching for hydrogen first orbit as 0.529 Armstrongs. Can you know, if you could recall, this is exactly what has Bohr's model suggested, that the radius of the first orbit is 0.529 Armstrongs. Okay. Same thing he has noticed here also, that the second peak value which has been found, this distance from here to here for hydrogen atom is found to be 0.529 into 2 square Armstrongs. So that is also about the second orbit. So the graph is giving so much insight that this peak value is suggesting where the electron can be present in a maximum time. That means the probability of finding electron at that particular peak will be highest. Got it? And second orbit's electron would be most probably found at this position most often. Of course, it will be present in other spaces also. The probability is less, but the probability higher at this point. Similarly, the electron of p, correct? The electron present in the p orbit will be present somewhere here. But of course, this is not something Bohr's have suggested, because Bohr's has only identified orbits but not orbitals distance. Okay. So from here the conclusion comes. Okay. First conclusion. What are these points exactly? What are these points? The points on those particular, on this graph suggest that there is a sphere around that nucleus on which there is no electron being found. Okay, clear? This point represent at this distance r, if you make a sphere across the nucleus, on that surface you will not find any electron. You will not find any electron of 1s or any electron of 2s, whatever that is the orbital. So that surface, that spherical surface where you can't find any electron, that is what we call it as a node. Okay, or in this case, because it is based on the distance, we call it as radial node. Let's check this out. Radial node, or also termed as spherical node. Okay, so what does that exactly imply? A spherical surface where probability of finding electrons, probability of finding electron is 0. Spherical surface where probability of finding electron is 0. Got it? This is called radial node. So for any orbital, if I want to find out the number of radial nodes, that will be simply n minus L minus 1. N minus L minus 1. Okay. So let me give you some examples here. Suppose I have 4D, I have 6F, sorry, 5F, I have 6S. For these cases, how much will be the radial nodes here? Right? So it will be simply 4 minus 2 minus 1. So which is 1. So in this case, 5 minus 3 minus 1. So which is 2. Here, 6 minus 0 minus 1. So which is 5. So there will be 5 radial nodes. There will be 2 radial nodes. And there will be, 1, 2 and 5 radial nodes here. What if I ask you to draw the graph of, let's say, 5F here? Now it's very simple. If I ask you 5F graphs, that means I'm asking you to plot for how does the psi square, and 4 pi r square psi square looks like. So I'll just simply copy from here. Check out how it will be drawn. So
Sir, it will be 1 for 5F, right?
what beta? For 5F? Oh, sorry,
It will
1.
be 1, right?
Sorry, 1. Thank you. Okay. So now notice this one. How do we plot the graphs here? So I need to plot for psi square, and 4 pi r square psi square. 4 pi r square psi square. So for any graph given, except for S, I told you that everything starts from origin. That's the easy way to remember, okay? Other than S, P, D, F, everything starts from origin only. Now, for 5F, we learned that there is only one node. So which clearly tells us that for here, it will start like this. It touches once and goes this way. That's it. And when it comes to psi square, it will start like this, touches once and turns around and goes like this. Because all you need to do is the negative part, you have to bring it to the positive side. And 4 pi r square psi square, it will touches only once, but the peak should be increasing here, increasing peaks. So once it touches and go like this and go this way. Done. So it's pretty easy. If you understand the pattern, it's pretty easy. Is this clear? Kapil, all good, beta? Any doubt?
No, no, don't think so.
Great. Swami, how about this? Soumya, did you understand, beta?
Yes, sir.
Right. Dave?
So I had a doubt. You said S orbital does not start from the origin. So in the
Correct.
above
Only
graph,
for psi and psi square.
okay.
Like this. Go back and check. Only in the case of psi and psi square, it starts somewhere from the point here, not from the origin. But if you take any other orbital, P, D, F, they all start from origin, all the cases. Okay. Okay?
Yes.
Right? So you can see, I'm just giving you a quick idea about that. So space where finding of electron is zero, that's what we call it as node. We have two types of nodes, spherical or radial node. Spherical, two names to it. Spherical surface on which electron is not found, or the number of nodes are n minus L minus 1. Okay. Now, what is the relevance or what is the terminology that we use here? What does exactly psi and psi square mean? Okay. Or do we have to go in detail about it? Honestly, no. You just need to know their idea. That's all. Okay. So if it is psi, okay, psi of, let's say, r here, so that represent here as the radial wave function of electron. Got it? Psi square, we call it as radial probability density, radial probability density function. Okay, clear? Or probability density function. Simply probability density function means we are talking about psi square. PDF, easy way to remember is PDF. Basically, radial probability density function suggests that, okay, what is the probability of finding electron at a point? Probability of finding electron at a point away from nucleus. Next, 4 pi r square psi square. Okay, got it? What does that mean? It is about total probability. Total probability in space. What do you mean by total probability? Or another important way to represent is radial probability distribution function. Okay, in general term, this is used as PDF and this is used as RPDF. RPDF. Yeah. PDF and RPDF. Clear? Now, what does this represent? This is about total probability is simply 0 to infinity across the entire volume. Sorry, you are integrating the psi square value across the entire volume, right? So that radial volume which you calculate is exactly 4 pi r square. 4 pi r square is the radius of the spherical surface into dr, correct, into psi square, correct. So that is total probability, everybody. Of course, you have to integrate that from 0 to infinity. Done. So I hope you understood the terminology as well. What is psi square, and 4 pi r square psi square? Any doubt here?
Sir, this the third graph will have two radial nodes, right? Or one?
Third graph, where is that, beta? You meant this one?
Yes.
No, it only depends upon the number of nodes. No, beta, there is only one node, correct? So it will only touch once. Okay. So we are plotting for 5f. Okay. If I were plotting for 6f, I will have to do it 5 times. 1, 2, 3, 4, 5, and then like. Okay. All good?
Yes, sir.
Correct. Now, let's now analyze what is angular analysis. That means angular part. Now we are talking about the angular part here. Yeah. See, when it comes to angular part, we were to discuss about if the r is constant, we are not changing the radius now. That distance we are not changing. We are only changing the angles, theta and phi angle we are changing. So if theta and phi angle are changing, correct? In that case, how will be the graph changing? That's what we are trying to figure out. Or, in fact, how does the shape of the orbital looks like? So this mainly emphasizes on the shape of the orbitals. Okay. So as theta and phi changes, shape of orbitals can be identified. Shape of the orbitals can be identified. Okay, clear. Now let me show you how. First one, there are two aspects we need to learn. First, for s orbital. For s orbital, we know that L value will remain 0 and M value, ML, magnetic quantum number, will also be 0. Okay. Then what has been noticed is that theta, I mean the theta of theta and the phi of phi, correct? Phi of phi. Okay, this is a representation of a function, by the way. Instead of writing f of and so, I'm writing this one. Theta of theta, phi of phi. This is the angular part. This angular part was found out to be a simple constant, which is 1 by 4 pi. Simple constant as 1 by 4 pi. Here. Now, what does this value suggest? The value suggests that it is s orbital is actually independent of theta and phi. So you would not see a case where you find just changing the angle and you might get, more probability or less probability or zero probability. Correct? Now, can you think about this case? When would that be possible that the at a certain distance r, the probability of finding electrons is constant or function is exactly same at all locations? That is only possible if the orbital is in spherical shape and the distance of that radius is fixed, isn't it? So because it is independent of theta and phi, we can say that the orbital must be spherical. Must be spherical orbital as theta and phi are independent values. Sorry, as the function is independent of theta and phi. Correct? Same thing when you notice it for p orbitals. So when you analyze for p orbital, doesn't matter whether it is, p orbital of 2p, 3p, 4p. No, n value is constant because these functions only depends upon L value and ML value. So p orbital, when it comes to px orbital, you know that L value is 1. I can take ML value. I can take the liberty of plus 1 or minus 1. Correct? Conventionally, px could be plus 1 or minus 1, but conventionally pz always is fixed, which is 0. Pz is always fixed to 0. So therefore, L value is 1, ML value is plus 1. In that case, theta of theta and psi of psi, this value is found out to be under root of 3 by 4 pi, 3 by 4 pi into sine theta into cos phi. This is the value observed in the Schrodinger's equation. Now, what does this value suggest? Can I go back a little bit? Go back and see when were we getting sine theta cos phi? When we were getting sine theta cos phi? When we are talking about x-axis. Right. Check out. We have sine theta cos phi, which means we are talking about an x component, right? So when you are talking about x component, it will not have any existence in z-axis or y-axis. When is it possible? Let me write down that and show you. Suppose if this is x component and this is x-axis, this is y-axis, let's say, and this is z-axis. Okay, x-axis, y-axis, and z-axis. In that case, if this is a value present in the function, I can say that must be an function which is observed only in plus x and minus x direction. It should not be found in y direction or it should not be found in z direction. And that's how when you completely write the function, it appears like a dumbbell. Okay, got it? So that is the shape which is got fixed here. Same way, if I talk about py orbital, py orbital where L is equal to 1 and ml is equal to minus 1, then theta of theta and phi of phi is found to be under root of 3 by 4 pi into sine theta sine phi, sine theta sine phi, and which is again suggesting the fact that this time it must be along y axis. The same orbital must be along y axis. So it should not have any overlap in x axis or z axis. Similarly, if you notice for pz orbital, L value is 1, ml value is 0. So theta of theta and phi of phi, right? This time, see, this time it is independent of these two factors. It is simply 3 by 4 pi under root cos theta. Again, go back to the coordinates, spherical coordinates. We write only cos theta when the function is about z component. Therefore, this is not how it looks like. We are talking this time about the function in z-axis. So this is a dumbbell shape across z-axis. Okay. So I hope you got an idea, like, how the value from the Schrodinger's equation helping us predict how the shape of the orbital looks like. Yeah. In the case of s orbital, it is purely observed in a spherical form. Now you observe in dumbbell form here. Okay. Well, honestly speaking, d orbital values you are not expected to mug up, but you should know how they look like. Okay. So these exact values, how they look like, that is not what is expected out of you, but at least you should know how it is being present at various orbitals. Now let me start with dz square first. Okay, because this is a value which is not expected for you to mug up, but at least you should know how does the value look like. Okay, that will explain you a lot of things about how the orbital is. Now before going into that, in p orbital, have you noticed something very interesting, that if you have to find out a particular plane where this electron density or this electron present in this double dumbbell is not present, then can I say that if you notice something carefully here, like this way, right? This is your xy plane. This is the xy plane, correct? I'm writing it very lightly. Notice this come properly here, correct? This is xy plane. Now I can clearly say that yz plane, my mistake, yz plane. So it is a yz plane. On yz plane, it is like, if this is a yz plane, this side there is a lobe, this side there is a lobe, and yz plane is dividing. It's like an uh, bisector, correct? So therefore, this yz plane is a plane on which px electrons are not found. So that is the nodal plane. So remember that. So when it comes to px, what is the nodal plane? Nodal plane. So nodal plane in this case is yz. So that also tells us that number of nodes, if you are checking out here for px, how many nodes we got? One. But what kind of a nodes we call? We call it as an angular node. So we call it as an angular node or planar node. Angular, or we can also call it as planar nodes. So planar node is one. Okay. Now the same thing I can observe that here in the second case, and observe the same thing in the third case also. But the plane is different. In the second case, what is the nodal plane, everybody? The nodal plane in this case, because it is going across y-axis here. Oh, sorry, I have to write it px, py, pz. I wrote the pz here only. Let me write down that pz here. Py got deleted some. See, let me rewrite the py value here again. Yeah, py was like this. This is py. So if this is py, you can see x and z. This is that plane on which electrons are not found. So this is xz plane. And when it comes to last one, the nodal plane is xy plane. So this is xy plane. So number of nodes are only one in all these cases. Whether it is px, py, pz, you get one node, one angular node or one planar node. Everybody clear? Yeah.
Yes, sir.
Good. See the next one. If it comes to d orbital has five different names labeled to it. One is xy, yz, xz, x square minus y square, and z square. Of course, it's not expected for us to learn all of this, but we know that how it is dz square. For dz square, this is how the function looks like. Okay. So again, you can notice the dz square is actually independent of 5. Is not, I mean, it is not dependent on 5. Clear? So if that, which clearly suggests that it should not be present, the lobe should not be present on x-axis or it should not be present on y-axis. It should be only present across z-axis. Okay. And another interesting fact here is, there is a lobe here like this, correct? This is how the lobe is, which makes xy plane as one, this xy plane as one particular plane on which electrons are not found. But this is a catch here. Problem what happened is, along with this particular lobe, there is one more lobe that is found as a circle in xy plane. Okay, as a circle in xy plane. Got it? It is found as a circle in xy plane. Enough. Go. Finish it. One second. So what has been noticed is that along with this lobe, there is a circular orbital that has been identified, which is on xy plane. So we can definitely say there are no planar nodes here, but still there are nodes which is not planar but angular. So what is that angle? For this particular lobe, if at all I make a cone shape here, on this cone shape you will never find any electron of dz orbital. So another cone shape below. So these two cones are the angular nodes. So remember that we do not have a planar nodes here. Okay. So no planar nodes observed. Observed. Okay. But number of nodes are 2. So how then what are these nodes? These nodes are basically angular or conical nodes. Okay. So number of nodes being 2, which is angular or conical nodes. Got it? Same way, this time if you notice for the other orbitals, okay? So dz square, sorry, dx, I'm writing it for function for dxy, let's say dxy. For dxy also you'll get some kind of a function. Again, like I said, we don't need to mug up. You just need to know that dxy, how does it look like? Now, when it comes to dxy here, if this is x, y, and z plane here, then the orbital will be along the, sorry, in between the XY axis here like this. So it will look like a dumbbell, double dumbbell, but it will be between the axis. So you can notice that it is between the axis. Okay. Similarly, DYZ and DXZ also look exactly same. They also look exactly same here. Just we need to change the axis. Okay. So now this time, this axis would be different. So this will be YZ and this will be X. And here this will be XZ and this will be Y. All of these would be showing double dumbbell form. And lastly, dx square minus y square. Dx square minus y square would be an orbital which is along the axis now. So it will go like this, along the axis, here and here like this. Okay. So that makes it x and y, and this is z axis. Got it? So this will be again a double dumbbell. And this is how the axis looks like. Right, everybody? Now notice one thing carefully. What is the planar nodes here? Because this will offer planar nodes here, correct? So you can notice that this x-axis completely here along the y-axis here. So this is x and y, correct? And if you take it this as z-axis going up, this entire thing is a plane on which you will not find any electron. Correct. So what is the planes where you will not find any electron? Here is two planes here, YZ and XZ planes. Okay, these are the nodal planes. These are the nodal planes. Okay, let me pull this slightly down here. Yeah, these two are the nodal planes. Likewise, here what are the nodal planes? Here this is XY, correct, and XZ. These are the planes which act like a nodal planes. And by the way, nodal planes are also angular nodes. Got it? So in this case, it will be xy and yz. These two are the planes. These two are the planes where you will see this as nodal planes. Correct? Then the last case, it is the plane passing through the center of it. So this is x and y axis center, and another one here, x and y axis center across the z axis. Correct? That we don't have to worry about writing exactly where it is, but you should know this is how the orbitals look like. Done? Everyone clear how it looks like? So the whole point of angular nodes is to figure out how the uh, orbitals are aligned, what is their shape, and what are the nodes they make. Clear? Now, see the last thing before I go to solving a lot of questions. So please check it out. Last thing here. When it comes to, let's say, I add the third shell. In the third shell, we have 3s, 3p, and 3d. These three are the orbitals we have, correct? So I'll do one thing. I'll just remove these questions for now. I'll add it at the end, okay? Need more space here. Check it out. So for this third shell here, what I can say for this third shell, in the case of third shell, when you plot the graphs, how does they look like? See, if I plot the graph, all the graphs I'm writing in one particular line here. See, this is for psi, okay, r of 3s, correct? And then I'm plotting it for psi r of uh, is it, if you have 3p, correct? And then psi of 3d, got it? In fact, I want to write this for 4 pi r square psi square, sorry, 4 pi r square psi square, 4 pi r square psi square, and 4 pi r square psi square, got it? All of them I'm scaling it to one particular graph here, got it? So how does it look like? See, first graph, the first graph would look for 3s. If it comes to 3s, we know that we need to have two particular touches here, like this, and like this. Okay, this will be the graph for 3s. Next, when it comes to 3p, in the case of 3p, we'll have one touch here like this, and then it will go like this. Got it? And lastly, when it comes to 3d, how does it look like? In the case of 3d, it will only have one particular graph which goes like this. Okay, what I'm trying to assess from here is, please check out these peak values. This is where the peak value is. Okay, next, this is the peak value for 3p, and this is the peak value for 3d. Got it? Now let's say this becomes the boundary of 3s. Okay, so which means if I put the actual structure of 3s orbital, this is where the nucleus is. Okay, let's say this is where the nucleus is. Let's understand that this is the nucleus here. Sorry, this is the nucleus here. Okay, now across the nucleus, let's say we have orbital like this. Got it? This is how the orbital is. And then if you notice, this is how the rest of the orbital looks like here. Okay, so this is how, let's say, rest of the orbital looks like. And when it comes to 3p here, that means this is how it keeps going around. And from here, I'll just correct it like this. So observe carefully. This node represent this particular space. This is the space. The second node represent this space. Got it? This is the space. So basically, this is that 3s orbital in which have these two nodes. So this is how it looks like. Okay. And second thing, when it comes to 3s, the probability, I mean, the peaks are coming multiple times already before it reaches to this higher point, which means electron would be electron density. I mean, the probability of finding electron closer towards the nucleus is more, right? So that means here you will find more electron density. While when it comes to p, there is only one peak coming before it reaches to this destination. And when it comes to 3D, there is only one peak at a lower distance here, which means if I take this particular point here as the final or the boundary of the 3s, that means electron density of 3s is more observed inside, slightly less observed for 3p, and very less observed for 3d. Correct? So that's the important note we need to understand here. For a particular n value, for a particular n value, got it? For a particular n value, you will notice that s orbital, s orbital has more penetrating power. Penetrating power. Penetrating power means what? Closeness to the nucleus, closeness to the nucleus, as compared to as compared to p and d orbital. So if you notice the penetrating power, penetrating power of a particular n value, it will be ns greater than np greater than nd greater than nf. That's why it's easy to easy to remove electron from nf as compared to nd, and subsequently and subsequently ns. Okay, so removing an electron from ns will be challenging, but removing an electron from nd or nf is easy, because most of its electron density is away from the nucleus, while ns electrons will be more close towards the nucleus. So very important concept. This is a concept which will build up its application more in periodic properties. Got it? But structure of atom helps us to understand the logic. Why we say penetrating power of S is more. Why we say electron negativity of S is more. Why we say removing electrons from P is easy than S. All of this becomes application in ionization, application in electron affinity, electron negativity. All these terms, all these parameters we learn in periodic properties. Okay, but you got an idea about, why that is being done based on the graphs. Okay, these are all based on Schrodinger's equation. Guys, have you understood this part now? Great.